on at the moment in Paris, which we're all very jealous of. So I'm very pleased. Philippe is going to talk to us about lots of field work he's done, working on a whole pile of things to do with subduction zones. He'll be talking to us, I'm sure, about the Alps and a variety of other places. He worked in Oman, Iran, lots of places. Without further ado, over to you, Philippe. As always, could you type any questions that you might have in the chat, and I'll read them out to Philippe at the end. Okay, over to you, Philippe.
Okay.
Oh, sorry, just one more thing. Just to remind everyone, this talk is being recorded.
Right. So there's that, no nasty questions. Is that what it means? So thanks Garrett, and thanks Valentin for inviting me, and thanks to all of you for being here. I hope you can see my screen. I guess the answer is yes, and you can see a view over to Mont Viso here. And today I'm going to focus on the record of how oceanic lithosphere was subducted in the Alps and what this brings to our understanding of subduction zones in general. One of the key, so let me just, I think it's about 40-45 minutes, right? If I'm correct.
Yes. Yeah,
so one of the key aspects in the Alps is that there are, in fact, quite many blue schists and eclogites, and many of you are familiar with those. They mean relicts of oceanic lithosphere that have disappeared in the Alps in a former subduction zones. And the thing is, there are quite a few in the Alps compared to other places, and you may wonder why. Another thing is, because we have those ones, one key question is, of course, to which extent are they representative of the subduction thermal regimes, or more generally of subduction dynamics? We can't, of course, drill down deep, so they are our best proxies in a way. So we'd like to know how strong or how good these proxies are. One of the specificity of the Alps is that it was a slow spreading ocean and a rather slow closing ocean. So does that make any change to the record? And as you can see, in general, I'm going to focus on what is exactly preserved here in the Alps, what it means for subduction processes. And on that, those pictures here, I've basically shown you two examples of fragments of oceanic lithosphere to the left. And of course, we'd like to learn a bit more about what subduction is doing and how this is happening at depth. And I'm going to focus mainly on subduction of oceanic lithosphere here. And last, we'd want to know whether there are any contrast across the Alps, and if this is maybe visible through the tomography. Many of you are probably familiar with the Alpes experiment going on at the moment. So just an overview of the Alps. What do we know? Well, we know a lot. It's just like the Thames Basin. It's been studied for 200 years at least, and you have all those units and a great complexity. Now, if I'm simplifying this tremendously and only looking at metamorphic rocks in the same map, same scale, you can see that there are quite a few metamorphic rocks spanning the entire core of the Alps. Let's look to the lower left here. The colors mean metamorphic facies, in other words, PT ranges. And you can see that there's a dominant color in blue and pink here, which is mostly found in the Western Alps, but also in some locations around. Whereas the red colors, which mean subduction, collision rather than subduction, are found mostly in the Central Alps and a few other places. So this is the result of a large-scale compilation in the year 2000s. And you can see those two types of metamorphism here. You can also see that throughout the orogeny itself. There are differences, of course, because as you can see from those cross sections going from the northwest here in the upper left to the east in the lower right, you can see how the architecture of the mountain belt changes. And that is also reflected, of course, in the metamorphic record. I'm not going into the details here, but you can find those colors in the metamorphic fascia superimposed on the cross section. That is to say, we know quite a few about metamorphism in the Alps and where this is located in terms of overall architecture. Regarding subduction, there's been some compilations, of course, prior compilations, the very same year. So here's the paper by Bousquet et al. 2008. I have to say it's probably been a bit of an inventory at the time, and there was also quite a bit of emphasis on the exhumation part, and I'm going to try and show you that maybe this is not all we can extract from the subducted fragments. And of course, since then, we've been, well, many more studies, including some of our group have been conducted in the Alps. So today I'm going to take you through the Alpine Belt. Let me simplify it and give you a bit of a reference frame here. Everything that's blue is oceanic. So all those blue colors mean subducted oceanic lithosphere, and in particular, the two mini basins that once existed in the Alps. One is the dark blue here, it's called the Liguro-Piedmont, and you can see it extend throughout. And another one, which is known as the Valais mini ocean, which is the light blue, extending again up to Vienna. In the middle, there was a continental block known as briocene, that's the orange part. And if you take a look at this simple section, which is somewhere here across Zermatt roughly, you can see that the structure is overall fairly simple, with the two oceanic domain here, the Valais below, the continental domain briocene, which was also subducted, and the oceanic domain here, all lie on top of one another beneath what is the upper plate, so that all these gray colors here, known as Adria or Southern Alps, Austro-Alpine, all these names you've heard before, I'm sure. And the downgoing continent, which is the Europe, with below the Penninic front here in yellow. All I'm going to present today is actually, I forgot to mention, comes from a recently published paper in Earth Science Reviews, one in Press and Elements, and a few others. I'm happy to discuss more details, of course. Now, if we try to go back to what it may have looked like, actually, if you simply unfold that section, you come up with this idea here that you once had subduction of Liguro-Piedmont ocean, that briocene continental fragment, and then the other Valais ocean here. And of course, going back to the first slide, what we want to know is not simply tell the story, but also learn about fluid transfer along the slab, any seismicity, whether it's more of a slicing and underplating, whether it's basal erosion, all these processes that we can try and study here in the Alps. So two oceanic branches, those units called Penninic, those ones here in color, and the upper plate, which is Adria. One of the peculiarities of the Alpine Ocean is that it used to be a slow spreading ocean. So on this picture here in the lower right, you can see the Valais domain, the Liguro-Piedmont, a fairly small ocean on the order of 700 kilometers probably at the most. Here we are somewhere during the early to mid Cretaceous, 120, 110. This is about when the spreading stops. You can estimate this is a fairly slow spreading, maximum probably 2 centimeters per year. And that is also reflected not only in the kinematic data, but in the rock record, because you can very commonly see exhumed mantle directly overlain by rhodolarian cherts, pelagic limestones. You also see ophiolitic breccias covering the top of the peridotites. So the slow spreading ocean, small. In other words, if you're trying to scale that to the present day, we might think of this as being the sort of distance between, let's say, Greenland and Norway, and a slow spreading domain. Let me show you this in 3D. Here is the cartoon showing what it may have looked like from the Western Alps going on to the Eastern Alps with those two oceanic domains. Further to the east, there actually was an ocean closing, which is a different branch of the ocean coming from, let's say, the Meliata domain. And you see 120, 110, this is when approximately spreading stops. And at some point, subduction will start and have this ocean disappear. If we now put this back into the timeline of the Alpine rifting and convergence, we know pretty well that during the lowermost Jurassic rifting started, expansion is thought to have lasted between 170 to 120, 110, and we know that subduction started somewhere between 190 and stopped by approximately 35 MA. So just to, for round numbers, basically half of it is extension, half of it is convergence and shortening. And one little thing I would like you to take a look at or remember is that the preserved ages of that subducted lithosphere tend to actually cluster around 170, 155 MA. And in other words, you don't preserve magmatic rocks formed on the seafloor that are younger than this, although we know that there must have been. Let's focus now specifically on the subduction history and the way we can tell what it did, how it happened actually through the subducted fragment. So here I'm just zooming in into the Western Alps where the high pressure rocks, subducted fragments are best preserved. And you can see that to match that map where you recognize those two oceans, I've labeled it with the metamorphic facies now. And you can clearly see that in the Liguro-Piedmont branch, the metamorphism increases towards the east and southeast, which is very general at the scale of the orogeny. And this is indicated that the former subduction zones actually dipped below Adria. So east deeping subduction zone. Another map here, same scale, showing the type of material which is recovered in the Alps. So from those oceanic rocks, you can see basically that there are two main types. The light green corresponds to dominantly sedimentary material, whereas everything that's dark is actually either mafic, let's think of basalts, gabbros, crust, or ultramafic, which is the topmost part probably of the mantle of the oceanic lithosphere. And you can see that there's a spatial divide, in fact, and I will show this again on the cross section, between the domain which is to the east, where you have mafic, ultramafic, and a lot of dominant metasedimentary rocks in the rest. And if you're trying to think about what that means, all this material has actually been scraped off the downgoing slab, and it means that these contrasts in material type argue for moments where the subduction thrust dipped into the slab. So you might think of normal subduction interface being here at the top of the slab, everything was sliding past, and at times what happened is that you stripped either chunks of sediments here, or obviously because you have those dark bodies here, you were able to actually strip down further into the slab and get thicker slices comprising not only mantle but gabbros and basalts. And I would like to emphasize that as well spatially. So here is the simple cross section from west to east, and you can recognize those colors. So those blue, dark blue corresponds to the Liguro-Piedmont here only on this transect. You recognize the orange briocene beneath, and you can see this divide here between the metasedimentary domain, which I noted S, and the mafic, ultramafic bodies here. So in the view, maybe some of you have been on the French-Italian border. Here would be the Colaniel, and you have a Sugarloaf here, which is actually a very nice walk. Mostly sediments. You can see the softer material, and the Mont Viso, which I showed on the first slide, which stands out as more robust, at least versus erosion. And the Pope Lane would be to the left. Sorry, this is actually switch. This is east-west and west-east. So that advocates for mechanical decoupling at various levels within the slab. And I like to emphasize that because I think this has been overlooked for many years actually, is when you're stripping material from the downgoing slab, it means that the main contact is actually jumping down into your slab. And to me, that advocates for strong mechanical coupling between the upper plate and the lower plate, at least transiently. And you might think of zooming into that and thinking, well, if I'm going to detach pieces here as the scissors represent, it means that at some point the sliding that you had along the interface is actually decreased, and you have a locking, transient locking of the interface, and nature finds its own way around this and basically dips into the slab and chunks get a piece of the slab. So mechanical coupling, and I'd like to emphasize that this is probably, of course, over, let's say, periods of a 10,000, 100,000, maybe up to million year kind of scale, but this may well represent also things that we see through the GPS record, and other people have been saying that those coupling could maybe extend across up to the million year. So let's go back to the Alps now. So just a few pictures of the sediments, so you can see those metasedimentary rocks, some with contrast between more carbonate rich, more pellitic rich. That also influences which type of minerals you have. So you see here the lawsonite in the more shaly parts. You can see the mum units, so very rarely do you see pillows that are not metamorphosed, so just slices that were accreted very shallow. Most of them you see pillows, those ones went to about 60 kilometer depths, and they're pretty pristine still. Those ones you can just recognize, and you can see the rims of the pillows that used to be hydrated, and this is probably why they have a lot of lawsonite, which is a water-rich mineral. And I'll go back to the Monviso here, where you have clasts of brecciated eclogite, which we think tell us about earthquakes in those environments. And this is probably now, if you remember my former picture here, this would be somewhere down on that side of the Monviso, watching, or let's say overlooking the Po Plain, which is here. You can see probably what is the best fragment of slab in the world, at least the one that's gone down to about 80 kilometers, where you see serpentinites here, you see gabbros, first magnesium, then iron titanium gabbros, and then basalts. So the entire sequence of the slab, almost pristinely preserved, and which offers privileged views throughout the oceanic lithosphere, of course. So now this is to sketch things briefly. I cannot go into every detail, of course. Let's try to see what it tells us in terms of the broader alpine view of subducted fragments. So here is all the main exposures of these rocks throughout the Alps. Again, you can see that in the western part you do have an even larger number of them. And I'm going to go through a series of conclusions that you can draw out of the rock record. So first of all, what you do see is that the very deep rocks that went down to about 80 kilometer depths are only found in the Western Alps. These are these pink to purple colors here. They correspond in that pressure versus temperature diagram. So in other words, depth versus temperature. It corresponds to these guys here, which corresponds to Monviso, Dermot, Sass rocks that you can see went to about 2.5 up to 3 GPa. In other words, up to about 90 kilometers. In contrast, you have all the sediments that seem to span a larger range of depths and range from something like 30, 40 kilometer depths, which is just down deep of the seismogenic zone, next to the moho of the upper plate in terms of depth, to somewhat deeper level down to about 60, 70, or even probably 80 at times. But overall, the main two conclusions that you have, not only in the Western Alps, but only in the Gros Piedmont, those eclogites, and overwhelmingly sediments are returned compared to the mafic crust. And although this diagram emphasizes that they could come from various depths, they tend to actually cluster around 30, 40 in terms of volume. Just pointed out here that the Ligurian Alps are probably somewhere below that diagram. I have not shown them, but they show very similar features. So this is somewhat of a busy diagram here. This is the same P and T here, slightly different scale actually. And let me get you oriented through the busy plot. So what I've shown here is actually all those dots corresponds to the worldwide record of subducted fragments for which we know the H confidently, the P and T, and basically the kinematic complex. And it's coded by size, which means those that were exhumed pretty early have very teeny tiny circles here, and the larger ones mean later exhumation and recovery. So in other words, you can see that early subduction is typified by a fairly warm, about 20 degree per kilometer, 25 degree per kilometer gradient, whereas then the system cools, and you can see that most PT conditions actually align along what I refer to as the mature subduction after about 5 to 10 MA, and which is along that 8 to 10 degree per kilometer here. This is for the background picture, and you don't get pieces exhumed from after that, and we may discuss that later if you're interested. So the Western Alps here are in blue, and you can see that there are some deep fragments. So those are ones corresponds to Montviso Zermatt. There is a range, but they span around 2.5 plus or minus something. Here is the sediments that tend to go shallower, and you can see the difference between the blue, which is the Western Alps, the Central Alps in black, and in gray the Eastern Alps. All of them, however, plot on this gradient, which is consistent with 8 to 10 degree per kilometer, given the plus and minuses that we have on the P and T estimates. So I think the conclusions is, it's been recently argued at times that the pressure recorded by thermodynamics might not be the actual effective lithostatic pressure, but rather reflect some lithostatic pressure plus some overpressure. In other words, there's been discussion as to whether those pressure represent depth and can be trusted for depth. And I think this is showing that it does, because if there was any tectonic overpressure, you would basically scatter all these units across different P in terms of overpressure, and there would be no consistent arrangement around the 8 to 10 degree per kilometer. This is not to say that it's impossible, because it could be like 10% overpressure is actually what we think for this little Chignana slice. But basically, the consistency advocates for the lack of any significant overpressure. Another reason is that whether the material is sediments or strong gabbros, there's a similar amount of P and T, so there's no rheologically controlled overpressure. And finally, if you walk around and you do the your field work, you realize that the P and T are consistent over vast exposures. So there's no reason why they would offset the points almost randomly, at least. Now let's focus on this diagram. This is probably the last very busy, although I'm not sure. And this is a very important one, actually. I'm just emphasizing on the subduction history. So that is the closure of the oceanic domain between 190 and about 30. In other words, that is about 60 million years of closure. And you can see that from the onset of oceanic subduction, this is time versus depth, you can see that the first half of the subduction history has left no trace. There's no subducted lithosphere, oceanic lithosphere recovered at the time. And it's only during the second half that you do see some fragments of two various types, actually. One is sediments, those guys here, which span a larger age range, whereas compared to the MUM units, the mafic, ultra mafic, which tend to be down the hole by 45, 43, depends exactly which one, and then come back pretty fast compared to the sediments. Continental subduction started, so Europe went down, the stretch part of Europe, that is the briocene, went down into subduction shortly afterwards, as you can see here, because this is the orange color, so Gran Paradiso, Monte Rosa, Doramera, remember those what we call internal basement complexes. They're very consistently down the hole at about 42, 43 and a bit younger for Doramera. So in other words, in that picture, it is very clearly showing us that nothing has been recovered from the early subduction stages. So 30 million years without anything, 30 million years with at least a few blue schists, and not much in terms of volume in any case. The mafic eclogites, those ones, the mum units, actually they're always associated with serpentinites. So the way we understand that is to say, well, they're not that dense. They are associated with some kind of a buoy, which is the serpentinized prototype, which is, as you may know, not very dense. And consistently, they were subducted down to about 80 kilometer depths. That's another characteristic. But not only that, but they also reach at the same time the greater depths. So in other words, those rocks were subducted not so long before, reached their peak burial, and then were off-scraped from the downgoing slab towards the end of oceanic subduction. That is probably when continental, if you think of a trajectory for the continent like this, actually the peak burial of the mum units more or less coincide with when those guys were actually up there and trying to subduct. The magmatic age is at about 170, 155. This is very important. This is the oldest fragment of the ocean. Remember, they plot here somewhere. And if you make a long story short, it's actually fairly simple to understand how the Alps opened up and closed at about the same rate. And if you think the first remnants, the first seafloor magma to form are the ones that are preserved, then you had expansion, and finally subduction came in, swallowed all the late portions of the magmatic crust, the latest forms, and then finally, towards the very end, did swallow those units that were formed first. So in other words, those units cannot have been formed very far out from the continent, and they are only remnants. So if you try and sketch that, and here I've scaled it, I think, reasonably precisely. So you have vertical depth, horizontal distances here, and here is the situation we are able to reconstruct at about 60 MA for those Western Alpine rocks. And you see that units like, so let me get you oriented. This is the briocene stretched continental margin. This will be the Dora Mera famous unit, which has coesite and the ultra high pressure conditions. Monviso, oceanic crust, probably discontinuous as in slow spreading oceans, formed about 80 to 100 kilometers away from the continent. And this is the part that was finally recovered. Everything down from the crust went down into subduction. Only the sediment, here shown as the dotted white parts here, did at times underplate. Some units were scraped off, and this is contributing to forming those S units, which actually were underplated before in the history. So all the big guys where you have the beautiful eclogites in the Alps corresponds to those that formed very early on in the oceanic stages and were subducted very last during the subduction history. So why is that? It's possibly related to the oceanic lithospheric structure. If you have a very discontinuous ocean, then you're able to actually strip parts that are just floating in the mantle in a way. They were located very close to the continent, so probably forming part of what is known as oceanic continental transitional domains. That does answer one thing, which is why those parts were selectively scraped off. And I think this is not a mechanical explanation, but at least there's a time coincidence between when those units were actually down to about 80 and when the continent here started to come in, and I'll show you a picture later. So the entrance of the stretched continental margin, in other words, may have changed something about the subduction dynamics and promoted the scraping off of those units. At least this happened at the same time. Now, having said this, you can basically go a bit further and go back to the first question. Now that we know roughly what the story is, a bit more precisely than before, we're also able to actually go and scrutinize the rock record and see what it tells us. And this is the picture at 45 MA, that is when the VISO here is at the greatest depth, around 80 kilometer depth. You can think of the plate interface being that black line here, so the upper plate mantle wedge here. And you have a discontinuous lithosphere going down, slow spreading, with mainly mantle, a few pods of gabbros, a few lava flows on top of it, some sedimentary breccias. All of that is going down and reacting to the subduction processes. And one of the things that we have documented is you tend to form not only do you rework the former contact, we also tend to form new contacts, and we've found some brecciation at 80 kilometer depths, which are good candidates for earthquakes in particular. So, by the way, I briefly mentioning that, you can, on that sketch just above, I've just highlighted those contacts which are inherited from the spreading or rifting stages, and in black here the contacts that form during the subduction history. So very same colors here. And some of the things we've been studying with Samuel Longiboost or Michele Locatelli in this particular context. And let's try and see, if we recap all the sort of studies that have been made in the Alps, this is how we should probably think of the Alpine subduction zone here. So in other words, you have this plate interface here in gray. You have some underplated sediments. Those are the S units I mentioned, so we can learn from them how tectonic underplating happens, what sort of fluids circulate here. This is the downgoing material, so sediments would be the white stuff again. This would be the topmost part of the mantle, strongly hydrothermalized, hydrated, serpentinized, in other words. Drier mantle below, and some gabbros and basalts on top. And you see, I'm not going into every detail, but of course, if that is the interface, you may want to look at pieces of slab like the one I've shown you in Mont Viso to try and fingerprint those tectonic slices, the fluid migration, and you can look for that at ages, rarest patterns, isotope studies, and so on, to try and fingerprint where these units are coming from. And as I can't go to any detail, but there's evidence for former seismicity. This is telling us something about the recycling of elements into the deeper mantle, and some constraints on the fluid migration. Just a few slides to tell you that it's not just the Western Alps. So here is a map of the Central Alps. This is Davos and St. Moritz here. This is the upper plate, the Angeline window. This area is known as the Grison. And over here, you can see again, those blue colors means the oceanic material. You can see that better in the cross section. On this traverse, you have more of the Valais ocean than you have the Liguro-Piedmont preserve, but both are there. And you can do the same kind of analysis, and you can use the P and T data of these units here, more or less cluster about 1.3 GPa, and you can restore what the situation looked like at the same moment, 6055, compared to what it looked like in the Western Alps. And you can see Europe here, the Valais, the briocene, Liguro-Piedmont, and a chunk of units here. The point I'd like to make is we know, and maybe some of you visited the area around Plata, and these areas are famous for preserving nice evidence of the rifting stages, necking, and all these processes associated with rifting. It's also very interesting to document what happened next, and in particular document the fact that there's been some subduction erosion here in this part of the subduction zone, which is not really seen in the western part. So it is confirming what I said before, that nothing was exhumed before about 60 million years, and some bits only afterwards. Let me just go back. I'm realizing that I forgot one thing here, which is this material here, the divide in time between lack of any fragment and recovery of some fragments is the subduction of Cesia. And the Cesia massif, I should have mentioned, is actually a part, and let me, sorry to moving you backward like this. The Cesia domain is actually a part that we think used to sit here somewhere outboard of Adria, so a stretched part of Adria. So before subduction of that, nothing is recovered. So sorry for this, let me go back to, this is of some importance. So let's go back to this, and let's now integrate that in map view again. So what you can do with all those characteristics, just looking at subduction oceanic fragments, you can see differences. I can't go into all the details, but they allow you to distinguish between various sectors of the Alps. So A, B, C, and D show different characteristics, which probably means subduction dynamics contrasts. If you add to that completely independently information coming from the internal basement complex, so I'm just putting in what is known as Monte Rosa, Gran Paradiso, Dora Meira. You recognize the colors. This means parts of the briocene which were very deeply subducted, and parts of the upper plate which was actually outboard and then subducted as well, which is Cesia and the Dent Blanche. You can see that this is actually again a divide, in fact, which it seems to be consistent with the divide I made just based on the oceanic fragment. So for example, in this sector A, metasediments experience a range of depths which is not seen elsewhere. The large-scale mafic units are much less developed here than they are actually in sector B. In sector A, you have the only UHP unit, which is just a thin slice in Dora Meira, 6-7 slices, evidence for a more stretched margin. Whereas here in the Monte Rosa and Gran Paradiso and in this transect, the continental margin to oceanic transition was probably sharper, narrower. And now I'm adding new details. So where are the prealps? Where is the Ivrea body? That is the deep part of mantle, which is very shallow in the tomographic images. What you do see is that the sector B appears to be, again, quite distinct from the other ones. So metasediments are always the same depth, large volumes of eclogitized mafic bodies, and those two guys, which are not UHP and went to only 2.2, 2.3, same depths as the oceanic material roughly. So what can we reconstruct from there? Just here drawn a sketch at 40 MA. In other words, that is just before all the oceanic material has disappeared. And this is emphasizing that at least half of the ocean has gone without leaving any trace. A good part of the rest has disappeared as well, and however we preserve some fragments, either sedimentary or mafic, ultramafic, if I'm just focusing on this part where it's most visible. Here would be the Adria upper plate represented, and again the sector A, B, C, and D. As you can see from the map, by the coincidence between where you find the deep exhumed rocks and the presence of the crystalline massifs that were subducted, you see a very good correspondence. So there's been a role in subducting peak fragments like the Cesia zone here. They've changed not only the subduction dynamics from no recovery to recovery of some rocks, but they also influence where you find them now. You can make differences across this elsewhere, so there's been evidence for subduction accretion versus subduction erosion elsewhere, B, C, and D. I think all of that is strongly arguing for the role of inherited features, be they what the margin looked like at the end of the Variscan orogeny, so contrast in crustal thickness, large-scale faults, That may also relate to the rifting episodes, so transcurrent faults, dissecting the margin, the type of sediments coming into the subduction zone, of course, or the magmatic structure of the disappeared oceanic lithosphere. But what I find is really striking here is that the contrast along the belt have actually persisted throughout continental subduction and collision, even to today. So, of course, today there's the Alpere experiment, so you might think, okay, what do we see of that at depth? And there's been, of course, tomographic images before, and now this is an in-progress version that was given to me by Mark Handy, and we've worked together a bit on this. And those hanging slabs, if you scale back things, it would be tempting to see them as oceanic material, but it's just impossible in terms of velocities and restoration. All of that is continental, partly detached lithosphere, and everything that oceanic is actually sitting down here in the mantle transition zone. Probably never actually really crossed the 660 boundary, and if you remember, that is due to the width of the oceanic domain, which probably was never more than 700 kilometers. So which depth that reached? Probably the mantle transition zone, but probably not deeper. And the interesting thing actually here is that I just kept the same boundaries, of course, sector A, B, C, and D, coming from the subducted fragments, and you can see that they seem to correspond actually to transitions that we see now at depths, even in the continental slabs, where you have a tear, where you have a partly delaminated material. So that confirms what I said regarding the persistence of these features. One of the puzzling thing in the Alps, of course, in the subduction history, is that there's no real volcanic arc, just a few rocks that are recorded here and there in sediments, but no real arc, so we don't really know very well why. Part of the reason I'm just suggesting this could come from the fact that it was such a slow sinking and short slab that in the end it may be that this alpine slab wasn't enough to actually trigger the counter flow and therefore heat transfer to melt the upper plate and provide a magmatic arc. So this is just a sketch that's coming from a recent paper related to the supra-subduction genesis of ophiolites, in particular in Oman, where I've scaled processes from what we know, and there's a time lag between the moment where you actually form the first melt and the future calcalkaline in any subduction zone. That's very well studied in the ESE subduction zone, for example. So it could be that this slab dynamics were insufficient to promote that melting. So I'm nearly done. In a nutshell, this is what the sort of vision I had before. I would say a simple vision as well, which is kind of probably still valid, with accretion of some sediments, the crust which only exhumed towards the end, and now this is collided after continental subduction, and this is what it looks today. I've shown you various snapshots of that, so 60 AMA for the Western Alps, 40 AMA, and finally the situation now. So it's about time to wrap up, I think. Just very briefly, the Alps, I think, are a fairly good proxy overall, and it's fortunately it can be used to assess the PT regime of mature subduction. So they can be looked at to see what sort of processes are actually acting in subduction zones, although it was a slow spreading ocean. The observation do not support the existence of significant oceanic overpressure. And I would say that it's, although there's a lot of it, it's not really exceptional. I think this is reflecting the fact that there is a bias in nature which tends to select slow spreading oceans rather than fast ocean. Having said this, of course, during half of the history, I've shown you that nothing was recovered, and overall, in terms of volume, not much was recovered of this oceanic material. I would say this is a at odds with, of course, the subduction of the fast ocean, like in the Pacific trenches today, in Japan, in Chile, where you don't actually recover anything from the subduction zones. And that is partly due to the, I think, the ocean plate stratigraphy, which is a thick, continuous crust, thick, continuous lithosphere. And this does not allow for the presence of many heterogeneities, serpentinites, buoyant material, all of which facilitate the stripping, or facilitated the stripping during the Alpine history. And I think, I'd like to emphasize that, I think those mafic fragments that we have, subducted material, we get more from the slow spreading oceans than we do from the other ones. So there's a slight bias towards that end. And I think the sort of rocks that, for example, Valentin Laurent's been studying in the Cyclades actually do also correspond to that. While the slow spreading ocean, fairly small, that's where you preserve the best eclogites, really. So one last word, I think the structural and petrological inheritance, as a conclusion, exerts a fundamental role on subduction dynamics and the potential for recovering them. In addition, of course, to anything that's happening during subduction, that is the interplate rheology, changing kinematics, and so on. And I'm just superimposing on top of that static view at 60 MA, what's happening next when the continental material is finally coming in. And just to go along the same lines as before, you see that here some of the sedimentary units were already underplated when all of a sudden those mafic, ultramafic Western Alpine units got scraped off at 80, from 80 kilometer depths at about 45 MA. And that is when the continent just impinges onto the subduction zone. So just to say that there are PhD students still working on the Alpine rocks, so whether around fluids in the seismogenic zone depths, characterizing the nature of those fluids and how deep underplating happens, or the contact here between the briocene and the schist lustrae, in other words, marking the continental to oceanic subduction. And I leave you here with this. Thank you.
Many thanks, Philippe. Oh, we're getting silent clapping from people. Another sad thing from doing these things remotely. If anybody has any questions, please feel free to put them in the chat and I can read them out. Maybe while people are thinking about that, I've got a couple, and I think they might be naive, I'm not sure. So talking about the rifting part, and I guess it's across, I think it's the briocene area where you get the serpentinites you were talking about. So I guess that sort of parasitic material converted into serpentinites, and then you get the radiolarian cherts on top.
Mm-hmm.
I went there once ages ago as part of, one of these discussions about rifting and whether rifting can be highly depth dependent or not. So like, do you really get through going detachments right down to the mantle as a way of generating pathways for fluids that could then serpentinize the peridotite? I wondered what your view was on that. I know some people now for the basin and range area, Nick Christie Blick, those arguments about having very low angle detachments as a way of extending continental lithosphere, he argues they're essentially, lots of those observations, I think I'm paraphrasing a bit, but lots of those observations he argues are now perhaps better interpreted as kind of large landslide type things. So you expose the lower crust, you expose the mantle without really having through going faults. And I wondered what your view here was on the rifting part. Like, do you think there's strong evidence for shallow detachments? That
I think it was best, actually, yes, this is reflected by the fact that we have exhumed mantle to the surface. Yeah. There are some people have even studied the nature of those peridotites and shown that not everywhere are they refertilized, but there are fragments that really look like, from the spinel chemistry and other pieces of evidence, they look very much like subcontinental mantle. So in other words, the picture goes that along the 700 kilometers you had, like 1/3, 1/2 was really astenospheric refertilized, but probably not more. Although, of course, these are just very rough estimates. Now, I guess where that's been documented pretty nicely is because it's better preserved, it's been less subducted. Sorry, let me go to that. Yeah, this is really in the Central Alps that people have been able to actually document those detachment going, preserving extensional allochtones here, and it's a good argument for flat-lying detachment. I'm thinking about the work of Manachal, Pforzheim, Muntener, and going to the Western Alps. This is true. You can see, sorry, here you can see the same sort of extensional allochtones, but you don't see the detachment so well preserved.
Yeah, okay. I get they're the H blocks people talk about. Is that right? H blocks?
The?
H blocks?
Oh, yeah, maybe you call them like that. Yeah. You mean edge as in EDG?
Like the letter.
Yeah.
Okay. I won't take over. I can catch you later about some of these things. We've had another question from Yigi Zhang. What are the assumptions of thickness of subducted oceanic crust? And a follow-up, is there any ambiguity of thickness based on the geometrical relations of facies here?
I think all we can say is that the thickest portions of crust are probably on the kilometer scale max. I don't know of any place where the crust itself would be thicker than about several hundred to max kilometer scale. Of course, this may have been disrupted by later tectonic evolution, but that is really on the maximum bound, I would say. And similarly, the most continuous part of mantle below that, in terms of thickness, would also be on the kilometer scale, and that would be near the Aosta Valley. So in other words, we have no clue as to how regular the thickness of the crust was. We only observe those big guys, and this is where we find the eclogites. If you extend the reasoning a little bit further, you may even think that everything that has disappeared during the first period of subduction may well have been oceanic material that was more regular crust, more continuous. Because it's all gone down, we don't know. So, but if you want to think, why would there be no fragments of that discontinuous crust being chopped off before? Well, either it has to do with subduction dynamics, which changed, or it has to do with the fact that the crust itself was a bit different.
More buoyant.
Not buoyant, because then, I mean, for the later stages, yes, maybe a little bit more, but that still doesn't explain why you recover them. It's not the buoyancy that recovers them. You need the trigger to actually strip those massif from the slab. They're not rising up back like diapirs or something.
Yeah. There was a follow-up, a question. The uneven thickness may cause some weird folding, tearing.
Well, that's the idea that I should have drawn it green in this particular slide. This is a piece of crust non-viso. Below is mantle, and if you think of that going down, at some point is going to be stripped here, which is shown here in this close-up view. This is actually somewhere what we recover now. I showed you a piece of slab which was mantle, gabbros, basalt. So in other words, the non-viso section corresponds to that. And you need to have the contact here somewhere rooting into the mantle in order to be able to detach a chunk of slab like this. So, yeah.
We had a question from Alex, which I think we'll have to make the last one, just because we're rolling on to 1 o'clock. So Alex's question was, can you comment further on the differing timescales of exhumation of the sedimentary units and the matrix ultramafic units?
Yeah, right. If the hidden question is regarding mechanisms, of course, I guess we all the existing data suggests that those sediments do indeed go back up slower than the mafic, ultramafic bodies do, about an order of magnitude difference. This has to do, I would say, probably with, if I'm trying to think of that, it means that those sediments are underplated shallow, about 30, 40, sometimes a bit deeper, and they travel back slowly. So this is probably telling us something about either relative buoyancy or rheology along the interface, whereas the Mont Viso and all these guys come up from deeper but faster. And whether that is to do with the difference in buoyancy between the surrounding mantle and those rocks, honestly, I don't know, and I don't think we we do for now. It's not, depending on how you calculate. If you want to put a lot of serpentinite below that gabbros, then you have a big buoy, but you don't know how much there was here to start with. So I still think this is a bit of a mystery. And I think over the last 30 years we haven't made much progress about how rocks are effectively being exhumed, and that's why I think is trying to focus more on what detaches the rocks could in the end be more promising.
Okay. Thank you very much. We're getting lots of thanks for the talk from a range of different people. Catherine, are you? I don't know if you're still there.
Not sure, because Catherine had another meeting starting at 1. But yeah, I think we can close this seminar. Thank you really much, Philippe. It was really, really, really nice. Yeah, as Gareth said, a lot of thanks and excellent talk in the chat.
Well,
Thank you very much. Lots of hand clapping, people. I can do your hand clap.
Yeah, thank you very much.
And a few of us will see you
in half an hour or so.
Half an hour, yeah. Lovely.
Have a nice lunch, everybody. And yeah.
Thank you very much.
Yeah, bye.
Thank you.
Thank you, bye.
Yeah, I think Philippe is gone. Yeah.
Yeah. Okay. Thank you for that. That was a good talk. Interesting.
Yeah. Really, really. So we meet in half an hour.
Half an hour. Lovely.
Yeah. I send the link, so everything should be fine. Great. Thank you, Gareth.
Thank you very much. Thanks.
Okay. See you.
Bye.